Hi, my name is Julia Silge, and I am a data scientist and software engineer at our studio. And in today's video, we're going to use tidymodels to implement principal component analysis using this week's Tidy Tuesday dataset about the BBC's poll on what are the top hip-hop songs of all time.
Okay, let's get started and use recipes to explore this data on the best hip hop songs of all time. So I loaded some of my setup information here, and then I got this data. So I'm using the rankings data from this week's Tidy Tuesday data set on this data set of hip hop songs. So if we wanted to take a look at what is here. So this is here are these songs that we have here, and so this is a data set of the BBC went to a set of music critics and asked these music critics to what were their 5 favorite rap songs, hip hop songs, and then they used like a certain voting strategy, and then made a ranking, assigned points, and then said what are the best hip hop songs based on this. So this is the title and the artist, and then here are the points that after talking to however many critics there were in the data set, the points that are here. And so this is the data set that we have of the rankings here. So let's explore this a little bit. So for example, let's recreate the plot that is in the source material. So that plot has a year along the x-axis, and then that ranking, that gender or that critic rating on the y-axis, and then it colors the points by gender. Geom point, and so we can pop that up here, and we can take a look at what this looks like. So this is basically what the plot looks like on the website that this data set is taken from. So you can notice that there's some of the most highly rated songs or from a while ago, and kind of notice how this is distributed. So there's a lot of songs that have a few votes and only a few songs that have a lot of votes. This is kind of a log normal kind of a distribution, and so I think let's plot this in a slightly different way. Let's put that y scale on a log axis, and some of these are plotting on top of each other. Let's kind of see what we got there, and we're starting to see where these things are plotting on top of each other. So let's, instead of geom point, let's try to jitter that so that we can see where these things plot on top of each other a little bit better. That helps somewhat. We're starting to get a better idea of where these things are relative to each other. So again, so now things aren't squashed all down there at the bottom of the y-axis, and we can see that yes, the most highly rated songs by these critics are all from like before the year 2000, from between like 1980 and 2000. And then the distribution looks of the stuff that's rated between about 1 and 30 kind of looks more even to me. So that's interesting. So we're gonna do a couple things in this video. We're going to try to get some features for these songs using the Spotify API, and then we are going to see if we can use those features to do any modeling. There's only 300 songs in this data set, so this is a pretty small set of data, but we're going to see what we can do. So we're just going to take a look and see what happens if we model those features directly, and then we're going to use recipes to do principal component analysis on those features, and we're going to see what we can learn by doing that, by doing principal component analysis. So let us see what we can do to get these audio features. So Spotify has a pretty cool API. There's a lot of stuff that is available in it, and there is a package called Spotifyer, which makes a lot of this available. So you have to get your own. You have to make a, let's load this. You make a developer account, a Spotify developer account, and then you can use, you get an access token, and if you access token like this, so if you, what I'm doing here is I'm going to my R environ file, and which is where my access token and secret and whatnot are stored, and so now R knows about that. So now R knows about my client ID and my secret, so that now I can access the information for from the Spotify API, which is fantastic. So there's a couple of different ways we could go about trying to get information here. So one that I was like, oh, that's going to be how I'm going to do this. There's a whole bunch of really fantastic functions that in Spotify are. One is this function, get the features and popularity for everything in a playlist. And Tom Mock put the 250 of these songs into a playlist. And so we could get all of these. So if we do get playlist audio features, and we put Tom, so there's two, we put his username, Tom's username here, and then we put this is the playlist URI here, and let's save this as something. So let's just call this playlist features like this. So if we run this, so it went to the API right then, and we went and we said, okay, so this is all for Tom's playlist that he made. What are all the features? And so the features are things like danceability and speechiness and instrumentalness. And we get here, we can say, let's pull the track name like this, and so we have a lot of these songs. It's 250 of these songs. So this is one way that we could match these up. But as you can, I actually think I'm not going to do this way because, for example, it's going to be hard to join some of this up. So I'm going to do. I think I'm actually not going to use this playlist. This would be a great if you just wanted to use the features. This would be a really great way to start if you just wanted to explore these features, like the acousticness and the time signature, and which is, I just love exploring all this stuff. It's so interesting. Look, like almost everything is in 4/4, but something's in 5/4. Boy, I gotta know what's in 5/4. Playlist features, filter, time, signature equals 5, pull, track name. Okay, all right. Very interesting. Okay, all right. So I'm actually not going to use this. Instead, let's use this function search Spotify like this. Search Spotify. So let's go down here and let's make a new little chunk. And let's show, this is going to be a demonstration of a way that I often write a little function and then use map to map from per to apply that function in a way that across, say, many rows of a data frame or in some way. So let's go back to that rankings and let's let's make ourselves a little search, a little search phrase, a little search a set of search words. So let's make a new column. Let's call it search or query, I guess. So search query. Let's call it search query. And let's paste together the title and the artist. So this will just paste it together with, so it's over here now with a space. And then let us search query. Let's make it all go to lowercase. I'm not sure if that makes a huge difference, but I think it's going to help. And all right, so so that's that. There we go. And then let's think about what do I want to do? So let's think about this search Spotify. So I need to look at one of them so I can put it in here. Select search query, like so. All right, here we go. So let's do this. So let's say search Spotify, and let's see what comes back. If I send this as the query, and then the type that I want there is track. I want to get tracks back. So this is what I get back, like this. All this. So let's just save this as an example. And what do I want to do? I want of everything that comes back from this search query, let's say I want the one that's most popular. Because you know there's all these different, like some of them are explicit and some of them are not, and some of them are from different albums, and some of them are there are a lot of different things that come back with this after this search query. But let's assume that the one that is the most popular is the one that is the real song, the song that I want. So let's arrange. I'm going to arrange by popularity. And then take the top one. I'm not going to use row. I'm not going to use top N because sometimes there are ties like this. And to get out, I think the thing that I want here is that ID, because this ID is that it's another Spotify URI like this, except now it's for a track instead of for a playlist. So this will say for this first song, the Notorious B.I.G. song, this is the ID right here. So let's start putting together a little function. So let's call it, I'm going to call it pull ID. And it is going to take a query. And then what's going to go in is this. So a search is going to search Spotify. And the query is going to go here. And then this stuff is going to go here, like so. And so this function isn't a good enough function to go into a package or anything, but this is a good enough function to use in a script. I'm not, name spacing or anything like that, but it's good enough to use in a script like this. Okay, so what I would do here is I'm going to say mutate ID equals map, and I'm going to map over the search query, and I'm going to say pull ID like this. So I'm not gonna do it for all 500 all at once. Let's just do the top 3 and let's see if it works. Oh well, it would help if I define the function, wouldn't it? Okay, so it worked. I made the ID. So it's of type list. Let's add something here so I can see the IDs. Let's say the titles and the IDs. Title, artist, ID, like this, so I can see it. Okay, good. So I know these are characters. So let's try mapping it to a character like that. Okay, Nice. So that worked. So I'm getting back these things here. So this is all working so far, which is fantastic. All right, let's see like what happens if I try to do a few more. All right. It didn't work. So what happened here is it got either number 4 or number 5, it failed. Like it didn't find, either it could not find something, like it went, like the query failed or something went wrong somewhere. And so I need to handle that case. And so the easiest way to do that, I think, is to use one of the adverbs in per. There's things like safely, quietly. Quietly just fails. It's like just do it and keep going. But I wanna put something in this column when it fails. So I'm gonna do possibly is what I'm gonna do. So I just wrap pull ID, wrap my function in possibly, and I say, okay, what do I do when you fail? When you fail, what should I give you? And I want you to give me an NA when you fail, like this. And okay, so it's this one is the one that fails, and okay, I bet that the artist in Spotify is Dr. Dre, and that it's failing because of this. So let's so I could keep going, right? But I bet this happens a lot in this data set. I could just keep all these NAs, but I bet that this happens a lot. So let's just try one more. Let's say what happens if I were to strip out everything after the feature. And see if that actually fixes this example, because there's going to be a lot like that. So what if I string remove from search query, and what if I remove everything, so FT, and then everything after FT. So let's see if I can do this without looking it up. Dot, star, and then everything to the end. So the end character. So this is like anything and more than one anything, and then that's to the end. So let's see if that worked. Let's see what the search queries looks like now. Search query. Okay, yep. So now it doesn't have featuring Snoop Doggy Dog anymore. And then let's see if, okay, great. So it did not fail this time. We found something in Spotify that matches. And great. Okay, so this will help not fail as often, is if we took the second artist, like the featured artist out here. All right, let's take out the head here and actually run it on everything. And let's call this ranking IDs, because what I'm doing is I'm taking the data I have and I'm getting IDs in Spotify for all of these. So let's run this. So there's 300 API calls here. I'm searching here. So let's I wonder how long this is going to take. I might need, let's see how this goes. So after what I am interested to know here is after I do this is like how often does this fail or not. So I'm gonna do something like what is the proportion of NAs. So I'm gonna say, so for this ranking IDs, how many of the IDs are NA, like this. So this will tell me what proportion is NA, and I actually can wrap that in percent, scales percent, like this, and that will tell me, I'll be able to say, once this finishes running, what percent of my data did I not find an ID for? And if it's low enough, we can just keep going. If it's too high, then we'll have to say, oh, we didn't match enough. We're gonna have to figure out, maybe do some other string handling or something here to be able to match things up and whatnot. Okay, the API just finished. So we've got our ranking IDs, like so. So we've got all of these IDs. Oh, shoot. I didn't mean to do, darn it. I didn't mean to select that. Let's see, what else do I need? Will that still work? ID, title, artist. I can still join up on title and artist, so that will work okay, I believe. Okay. Okay, so let's see, how did we do? Okay, so 6% are missing, and so in our ranking IDs we have, yeah, okay, so how many? So let's say some ranking IDs, some not is NA ranking IDs ID. So we've got 293 songs for which we have an ID. That's okay. I think that's okay, and we can keep going. All right, so we have the IDs. Now that we have IDs, we need to get the audio features. So I showed how to get it for a playlist up here, but you can get it for an individual track as well. And that's what we're gonna do. So the reason audio features like this. So the reason we are not using the playlist is because we can't match it up to the rankings. So that's why we're doing this individually, and also to demonstrate how to use to make a little function and use map in this way, which is a useful workflow that I use a lot. Okay, so we've got these IDs, these ranking IDs, like so. Okay, so it turns out, let me see what we've got here. You can only send a maximum of 100 IDs to this function at a time, and we have got 293. So we're gonna have to do this in chunks. So let us divide this data frame up into chunks. So let's make an ID group column. So it is going to let's call so we're gonna take the row number and do like floor division, and let's see what happens if we do 80 like that. I think that's gonna work. So then if we just select the ID group and the ID like so, and then nest like this. Let's see, we can say, I think data equals, oh gosh, no. We want data equals, we don't want to nest everything. We want to nest, minus ID group, like so. Oh yeah, sorry, data equals CID. Like this. So we nest in this way. Okay, great. So this, yeah, 80 is nice. These are each, 79, 80, 80, 72. So we've got now like the 4 chunks. We're just doing it in 4 chunks because we can only send at max 100 at a time to get the audio features. So that's why we've divided it up in this way. So we've got our nice chunks here. And now what we can do, whoops. Is now we can map again. So let's get our audio features. And so we map, and now what we're mapping onto is this data column. So map data, and then what we're going to do is that get track audio features, and we need to get into this little column that's inside there, and it is, so we're going to need to do it like dot ID like that. So we need to make it a lambda like this. So let's call that ranking features like so. So we're going to do this. So we're doing 4 API calls this time. So that's, oh, I misspelled it. Let's do it again. There we go. Okay. Ranking features like this. So this has the IDs in it, and then this has those audio features like what we saw before, like danceability and loudness, and like whether it's a major or minor key and whatnot, things like that. Okay, so let us start to get this all together. So what will we do here? So we've got the ranking IDs, which oh man, this was a mistake right here. Unfortunately. So we're gonna have to, let's see. You know what? I'm just gonna run this again one more time, and I'm gonna just quickly, and I'll edit the video one more time so you don't have to sit through it. Okay, that ran. Whoops. And we are back. And we have got this, which now has the ID connected to all this other stuff, which is what we want. So let's start joining this all together and making our data frame that we're going to use for modeling and principal component analysis. So we've got the IDs. Let's filter out anything that did not get an ID. And let us interjoin with some stuff over here with the features. So ranking features. So first, we're gonna select that. Let's see. So in the data, let's see. So wait, what's in the data? Let's remind myself. That's just the ideas, and we already have that, so we don't need that. Instead of interjoining, we're just going to bind the columns. Is that right? Are these all in the same order still? I believe so. So let's double check that this is right. So unnest. So let's do the audio features. And let's select audio features like so. Okay, so this, we've got, there should be some NAs in here. Let's view this. Yes, okay. So there's NAs in here. Okay, so we do not want to do the NA filter. We are going to bind at this point. So we're going to bind the columns with this thing right here. And we are going to make sure that the NAs line up. I am pretty sure this is all staying in the same order, but just to make sure, let's make sure that the NAs line up. They do. Okay, so this all stayed in the same order, so we are good to go. And I wonder what is happening with the NAs. Yeah, it's just some things that are spelled differently. Yeah, and some things that are yep. Yeah, so I'm not gonna worry about fixing those, but it makes sense why those search queries did not work. Okay, so we have now bound those columns together, and then now let's start to think about what here do we want. for our principal component analysis and modeling. So let's keep title and artists around so we know what is what. Points is the thing that we would like to, understand. What of these features can we understand anything that about these audio features that are more associated with higher critic scores? So we need the points. Let's keep year, because that's the only thing so far that we do see any change with. And then let's look at those features. So let's keep danceability through. So energy, key is literally the musical key, like, C, F, G, E flat. So loudness, mode. I looked up in the API docs, and that's whether it's a major or a minor key. Speechiness, which tends to be higher for hip hop. Generally, acousticness, instrumentalness, liveness. Valence is a measure from an audio perspective as to how happy the song is. So this isn't a measure of sentiment analysis. It's not to do with the lyrics, but it is a measure of how happy the song is. Tempo, and then type, I think, is we don't want. So type is now to like an audio thing. So we don't want that. So we want danceability to tempo is what we want. And let's call this ranking DF, like so. All right, there we go. So this is, and now let's do the filter. Filter, I'm not is NA ID. Oh, well now ID is gone. Let's say, dance. I mean, we could filter. Let's say filter NA omit. We'll say NA omit like that. Ranking DF. Okay, this is now the number we expect to have. Excellent. All right, so to try to understand what's going on with this data, let's see if any of these things are correlated with each other. So I'm going to use the core package, which is part of tidymodels, and I am a big fan of it. I like using it. So let's take this ranking DF and let's select the things that are these numeric things. Let's not look at points yet, but let's take like year through tempo, year to tempo, and let's pipe to the main function, which is correlate. So I gotta load that. Okay, so what we have here now is like is all the correlations between all these things. And we've got NAs on the diagonal, of course. And so looking at these, none of these things are very high, right? I don't see any huge numbers, but to make it easier to look at, we can rearrange. That just reorders things, like which order these things are in by the correlations. And then we can also, the other thing I tend to do is this shave command, which just gets rid of one of the triangles. And now we can see most of them now, and we can start to see that, yeah, these numbers are not very big. So we don't see super high correlations here, but it would be easier to visualize this. So let's make a plot. This is just a ggplot2 plot, so I am going to add my theme. That is my theme I like to use here, so I can look at it. And just in case you're interested, I tend to like to look at them as squares better, and I also instead of that thing with the colors, well, I mean, if you want to change the colors, like say you want to do orange instead of, and you can change the colors in this way. This is how you change things in this if you want. So let's zoom in and see what we have here. So a lot of stuff is not very correlated with each other. There's not a lot of color on this plot because a lot of the correlations are very close to zero. Energy and loudness are somewhat correlated with each other. And along year, we see year and danceability are anti-correlated, and valence. So like the older songs are more danceable and happier, and year is correlated with loudness. So newer songs are louder. So we see some of these like correlations, and nothing is huge, right? But we see some of these relationships, and what we're going to do with principal component analysis is try to take advantage of any relationships that are in here to and see how much we can measure these things. Before we do that, let's see, before we perform the principal component analysis, let's see if we take that data frame, let's take off title and artist, which are identifiers, and let's just fit a simple model. Let's fit on the log scale for points. And let's say data equals dot. That means I'm piping in the data. And let's call this ranking on LM. And then let's just do summary on it. We're gonna, I guess, kick it old school here. I'm not using parsnip or anything here because we're not doing anything. I'm literally only doing a linear regression. So. There you go. Okay, so when I just fit the features directly, the only thing we see any impact from is the year. That's the only thing that is a predictor that has a p-value smaller than 0.1 or anything like that. So in the fact that like older songs are more likely to have the higher scores from critics. So that's the only thing we see here. So what we want to do in performing principal component analysis is are the relationships that we see among these different features. Do we see something significant there? It's not each of these individually, but rather the relationships between these different things. So let's do that. Let's get started here. I know that was a lot of non-tidymodel stuff, but I like showing that because it is that per map make a little function workflow is something that I find pretty useful and do a lot. But now it is time for tidymodels. Okay, because we're going to use recipes to do principal component analysis. It is I've done principal component analysis in a lot of different ways over the years, even from before my R days, and this is just a really lovely way to do it that I really like. So we build a recipe. And so the recipe here, we are going to build a model with this. So we build the recipe where we say, I want to explain points by everything else. And my data is, this ranking DF. And I am going to then start adding steps to my recipe. So my first recipe there is always, my first thing I do with my recipe is always define like what is my model and what's the data that goes into it. And now let's update the role. Update role here for some of the, if you remember what is in ranking. These first two things are not things we're going to use in the modeling or the principal component analysis or anything. So let's say new role equals ID, like that, because we don't want those in the principal component analysis or anything like that. The points, I don't want to, I want to take the log of it, so I can say step log like this and say points. And now let's do step normalize all predictors, step, and then step PCA all predictors. Like so. So this will be my ranking recipe. Like that. Whoops. Like so. So there's my ranking recipe. So this is a definition of my recipe. And if I want to actually learn the learn the components and whatnot, I need to prep it. So I will prep the recipe here. Ranking, whoops, prep, like so. Ranking, prep. So we did the centering and scaling, and we performed principal component analysis for all the things that we were interested in. So and now we can go and we can explore the results of the principal component analysis, and then we can use it in a model. So let's explore the results first. First, let's say, like, what do the components look like? So the way that you get out the results is by tidying them. So we would say ranking, prep, and then, so what happens if we tidy the whole thing? It tells us how many steps there are. And then you get out the individual steps by giving an argument. So we can say 1, that's taking the log. 2, this is where we normalized. And then 3, this is the principal component 1 here. So let us call this tidied PCA, like that, because we need to keep that. And then what we can do is make a visualization of this. So let's take the tidied PCA, and so let's see, what do we want to do? Let's put value on the x-axis, terms on the y-axis, and let's fill for terms so it's easier to compare. And geom call. We will not need a legend. And let us facet wrap like so. So let's see how this does. Okay, our components are not quite in the right order. So let's but they're in the right order in the data frame. So we can just do this. And let's, we can certainly at least get rid of that. There we go. All right, so let's take a look at this. So this is the first 12 components. We can take a look at, like, how are things contributing? What's contributing to these different components? The first, second, third principal component. So year and danceability are contributing a lot to the first. Energy and loudness to the second, and we can go down and see, like, what's contributing to them. I like looking at this plot. This is with the different components in the same order here. That's pretty helpful as an overall viewpoint, but it is nice to zoom in into the first couple. So let's say tidied PCA, and let's filter. Let's start maybe with the first 2, like this, and let's see, how should we do this? So let's group by component and take the top. Let's say to the top 6 by absolute value, and then ungroup. And then let's start a plot here. So we're going to say, let's put the absolute value on the x-axis, the terms on the y-axis, and then let's make the fill whether the value is positive or negative, because we're gonna plot the absolute value but color it as to whether it was positive or negative. And so we're gonna be able to say like what's the biggest contributor by just size, and then let's facet wrap by component like so. So let's see what that looks like. All right, and then let's say scales equals free y. All right, so that's looking pretty interesting here. If we can actually get these in order here as well. There's a little set of functions in tidytext that does this. So we can, here, let's mutate terms. It's called reorder. Well, I got all this loaded. It's called reorder within. And so we're going to reorder terms by the absolute value of the value within component, and then we are going to oops, I messed something up. I got a pipe. There you go. Scale y reordered like this. I believe this will do it. Yeah, nice. Okay, let's add a couple more. PC3, PC4, and these labels are not so helpful. So they're on the x-axis. Let's call it. So what this is it's the absolute value of the contribution of each of these to each of these features, these audio features. Okay, so what we have here is and what that fill is it positive, or is it in the other direction? So for the first principal component, the thing that explains the most variation in these songs is it an old song or a new song, and how danceable is it? The second variation, and then these other things, how happy is it? How loud? The second variation is it a high energy loud song? Or not. And then the third is it is a speechy song or not. And then we can keep going down. And then fourth, that's kind of interesting. The fourth one is like, mode is like the major minor key thing, and what key is it in? So that's, this is kind of about the actual musical characteristics of it. That's pretty interesting. Oh, nice. Okay, so that's pretty interesting. So that is what are the components that contribute to these songs. We can also look at where are things distributed in these planes. So if we go to ranking prep and we juice it, ranking prep like this, what do we get out? We get out for all of these songs. Oh, very nice. The first song is juicy, and we just juiced ranking prep. I like it. So we get out these the first several principal components, and where in those planes are each of these songs. So we can just plot any of these like super conveniently. So let's say PC1, PC2. I'll say label equals title. Like this, and let's start just by putting points. I think there might be a lot of them, so let's do this, and let's just do that. Okay, so let's remind ourselves, principal component 1 was how old and how danceable these songs were. So positive was new songs, less danceable songs. Negative was older songs, more danceable songs. And PC2 was energetic, loud songs up here, and quieter, I guess, less energetic songs down here. So it's definitely very smoothly distributed, which is interesting. Let us attempt. This is 200. This is 200 things, so this isn't going to be great. Let's put the text on. Yep, not great. We could try GG Repel, but it's 200, it's 300. I mean, it's not going to work very well. So let's just do this. The downside of check overlap equals true. And I'm going to share something with you all. I hate looking at plots that have mismatched fonts. I know. I don't like it. So let's now all the fonts match much better. Okay. All right. So now let's look at this again. Okay. So we are not looking at all of the song titles, because when they were going to overlap, it just did not plot it. So things on the right are newer and or less danceable. Things on the left over on this side are older. Here's Rapper's Delight, and or more danceable. Things down here, like No Church in the Wild, is like lower energy, quieter. Things up high are high energy and louder. Which, yeah, I'll buy it. I think it did it. And we can change these, for example, to these other things like PC3. Am I forgetting what PC3 is? PC3 was, I literally have forgotten. What was it? PC3 was, speechiness. So this one shows us, so same thing here, old to new, and now we have more speechy to less speechy. Or more speechy to less speechy, this way. Which is, again, I can see it. I get it. Interesting. All right. And we can keep going. We can go through and like look at any of the components that we would like that ended up getting juiced. Okay. The other thing that we usually would like to know with principal component analysis is how much of the variation in these songs are we capturing with a certain number of components. This one, I'll be honest, isn't fantastic how you're getting this out. So this is a prepped recipe, and you can get out the steps here. Here, all the steps are in here, and so you can go to the third step, which is our PCA step, and get out the results and get out the the standard deviation like this. So I know that's like not a very tidy thing, is right there, is it? That's pretty. Oh well, what are you gonna do? Let's call that the standard deviation. And then so we've got the standard deviation there, and so if we take the standard deviation and we square it, and we divide by the sum of the square, right? Am I doing this right? Yes, that's a scalar. That will give us the percent variation like this. So this is a vector. There we go. Oh wait, Let's make sure that worked. Yeah, okay, great. All right, so the percent variation is a vector like this, and we can make a little quick visualization to look at how the variation, what percent of the variation we're capturing in each of these components. So we could let's call it component, and we had that in tidied PCA. Here it's in component, so we could say, let's say unique tidied PCA component, and then percent var, let's just call it this, and let's just do this on the x-axis, percent on the y-axis, and make a nice little bar chart like so. It's out of order again, so let's do the same thing we did before using fact in order component, and let's put on the y-axis scale continuous. These are percents, so that's always kind of nice, like so. There we go. And if you wanted, we could do sum here, cumulative sum here, and we could, make like how much is it cumulative, instead of, depending on what you want to see. Like, do you want to see individually, or do you want to see, cumulative sum there instead, which would be great. All right. I think let's do one more thing here here at the end. Let's take this like so, but let's do a PCA LM, and instead of the ranking DF, let's fit that juiced data like this. And the log has already been taken. So I'm just going to show to remind you the juice ranking prep. What I'm showing you here is really how recipes is used for data pre-processing. We use recipes to pre-process our data here, and it's all very nice and ready for us here to fit a very, very simple model here, but a simple model here ready for us to go. But we do the same things here, but we do not need to take the log because I took the log in the recipe. And let's see what we got. Okay, all right, so we now at a somewhat, we have some evidence, perhaps we could say we have some evidence that that this principal component is associated with higher critic scores. And so let's remind ourselves what PC1 is here. So PC1 is the one that's years, and so it's negative. Notice here that the the coefficient is negative. And so that means that older songs and these songs that are older and more danceable are associated with higher critic scores. So that's it basically. Like when we do this whole this linear algebra and all this, and that's all we got here at the end. So perhaps when we look at if we were to say look at this plot and, you know, put the labels on what these things were up here and here, and be like, oh, look, those songs are older, and they, you know, like, and those songs over there or have a are happier, more danceable songs. And perhaps you could have said the same thing, but now we did it with math. So I'm glad we got to do that together.
Okay, we did it. We used tidymodels to implement principal component analysis using the audio features that we got from the Spotify API, and we saw that which of the features were related to each other. That older songs were more likely to be more danceable and to have higher critic ratings. So I love using tidymodels for principal component analysis and be able to easily visualize the results afterwards. And you can use, and this was a really great, I feel like, demonstration of how to use recipes for pre-processing your data for modeling, for whatever kind of modeling you need to do afterwards. I hope this was helpful, and I'll see you next time.